Well, in most of my videos, you see me writing on a pad, and I think in this case, because I like the images that I could find, I'm going to just use a couple of slides here to show you, because the concept is pretty straightforward. I just want to show you examples of what we call conservation of angular momentum. Now, if you think back to your other conservation of momentum problems, they were typically maybe masses or carts that were moving along a track, and they would collide with each other, and sometimes they would stick together, sometimes they would separate apart. But the whole idea was if we accounted for all of the momentum before they collided, that it would equal all the momentum that they had after they collided. And then we could just solve for whatever was asked. And these particular problems will have a similar kind of flavor. So if you look at the figure here, this is like an old vinyl record being plopped onto a turntable. But I think if you're familiar with a turntable, you know it's got a little motor that makes it move. I want you to imagine that the motor has been turned off, so that turntable that's turning is just kind of turning on its own. And that'll help you kind of make a more realistic example. So if we have the record just hovering above it and then dropping onto the moving turntable, we're going to conserve the angular momentum. Again, we're turning the motor off so that nothing is trying to add momentum while we're trying to conserve it. So we usually start, use my cursor here, we usually start with just this form here, showing that all the initial angular momentum, remember that's the symbol L, is equal to all the final angular momentum. And when we're dealing with objects where the mass is spread out over a wide volume or shape, then we use this expression here for the angular momentum. It's the moment of inertia for the object times its angular velocity. So let's think about what would have angular momentum before these things collide. Well, it would just be the turntable. It's got its moment of inertia. Maybe we could use the formula for a disk's moment of inertia, and then we'd have to know what the angular velocity is. We just multiply those, and that would be that. But the record, even though it's moving straight downward, that does not give it any angular momentum. It does certainly give it some downward linear momentum, but none of that would be considered angular momentum. So we would just have 0 for the record part. So this would just be for the disk. Well, what happens after they collide? At that point, once they're coupled together, we have to imagine that the hole from the record falls right onto the little spindle here on the turntable. And if that happens, then both of these objects will be moving together. Again, you got to use your imagination a little bit. Imagine that maybe there's like a little rubber plate that this sits on so that it sort of grips the record, and then everything ends up moving with the same final angular velocity. Otherwise, we'd have the record kind of slipping on top of the moving turntable, and that doesn't happen. So we would now have a moment of inertia after the collision that would be the combination of the record plus the disk. So this final I number would be higher. And if we're going to conserve momentum, that means that our angular velocity number is going to have to be lower. So putting this in plain English, all it means is that this turntable is not going to spin as fast after the collision as it did before the collision. A lot like an inelastic collision where you've got a stationary object and it gets hit by a moving object. The motion of the moving object definitely slows down as a result of that collision. So that's one form this can take. Here's another form this can take. And this is actually a really common one. You see this a lot in figure skating. So we have, looks like a kind of a nerdy physics teacher, and standing on a freely moving turntable with some barbell weights way out to the side. And we do that because we want to give this person a very high moment of inertia. So remember, the farther away your mass is from the rotation axis, the higher the moment of inertia. So we got a high moment of inertia here. Somebody gives him a little spin, so he's got some initial angular velocity, so that would be all here, I times omega. But now, instead of a collision, suppose the man pulls the weights inward. That means the moment of inertia for the man is decreasing. So when we look at him at this particular point, the I number is smaller, which means what? If angular momentum is conserved, then the omega is going to have to be higher, and this person's going to be spinning real fast. You'll see this at the end of a lot of skating routines where the skater will pull their arms inward, causing the spin to increase. It's kind of a dramatic ending. And then when they want to stop, they shoot the arms outward quickly, and the angular speed diminishes very rapidly as well. So this is actually a great demonstration. I like to do it for my students on a little stool that I have that spins around, and it's kind of fun. It can be dangerous if you're not careful. If you have, let's say, a desk chair, something that has the ability to spin, maybe get yourself some heavy weights and try this yourself. Just have somebody give you a twirl around. But I do want to caution you to be careful, because you can fly off the chair quicker than you can probably imagine. That's kind of a fun way to demonstrate for yourself conservation of angular momentum. Now, I should specify one thing. You might be saying to yourself, well, why does the momentum even have to be conserved? And really, it boils down to this. If there are no outside torques pushing or pulling on the system, that here in this case would be like the weights and the man and the stool, if nothing from the outside gives it a shove that makes it spin differently, then momentum, angular momentum that is, will be conserved. So you got to imagine there's no other people nearby, nothing like that. It's a freely moving stool. So we don't have, even friction cannot exert a torque. So everything here is internal, and therefore angular momentum will be conserved. So there's two real common collision situations, or I shouldn't call them both collisions, just some kind of changing system with conservation. There's one last kind that I'm going to actually do in a separate video. It's real common too. The AP folks love this. It's when you have something moving straight and it hits something that's able to spin. So I'm going to call that combining linear momentum or linear motion with spinning motion in the form of a collision. So tune into that if you see that sort of problem. Thanks for joining me. Hope this was helpful for you.